Hello everyone and welcome to another video, this time doing step 1 2006 question 10. So this question is a projectiles question, which I think is good practice for people to do, particularly if you're doing step 2 and step 3, because in step 2 you'll have a projectiles question there, probably, and you'll have like some kind of wonky moments there, question there probably. And that's because step 2 is mostly A-level maths. I think they're allowed to put further maths AS in there, I think, but it's as a result of that, the mechanics section will be heavily influenced by the mechanics A-level. And what's difficult in the mechanics A-level? The normal A-level, well, the projectiles and the wonky moments. So they tend to do questions on those two topics. But don't believe me, just have a look at the most recent papers and see if you agree. I think it's true though. And the great thing is there's loads of old projectiles questions on step 1 and step 2. So yeah, you can find lots of examples of these. Don't think, if you go into the step exam thinking I'm only going to touch the pure, you've limited your opportunities, haven't you really? That's crazy. You want to have, at least one side of the applied, which you might be tempted to dip into. That's what would be my recommendation. So I'm going to show you some applied step. Okay, so here we go. What do we got here? Now, it's wordy, that always puts people off, but it's not that bad. Particularly the first part, we've just got a projectile, which has been projected at 45 degrees angle. Okay, with speed v. So straight away I can say my initial vector, which I always do this in vectors, but if you consider the x components and the y components, it's the same thing. Yeah, I'm just going to have v over root 2 in the x direction and v over root 2 in the y direction. Yeah, and so those two components will give me this vector. A is always nothing, no acceleration in the x direction, but acceleration downwards at the speed of gravity, which is 9.8 meters per second squared. Did I say the speed of gravity? That's really the acceleration. Okay, so we've got U and A, and they're always the same on these questions. What else do we know? We know we've got to find the, here it's asking for the equation of the trajectory of P. So it wants, if you like, it wants y in terms of x. That'll give us the equation of the trajectory, basically the height in terms of the horizontal distance travelled, or the other way round. I'm going to do y in terms of x because that's traditional, and I'm just going to put t equals t now here. Okay, so looking at this, s equals ut plus a half at squared looks like a good idea. And you might think, well, why did I put t equals t? It's just because both of them I can express in terms of t. So for example, x equals vt over root 2, whereas y equals vt over root 2 plus a half at squared, which in this case is minus g over 2 t squared. We didn't have that bit on the end for the x component because that is 0. Or if you prefer, this is really just distance equals speed times time, isn't it really? Because there's no acceleration. When there's no acceleration, you can use speed, distance and time. Okay, so what am I going to do next? I'm going to eliminate t. Well, t is obviously root 2x over v. And so I'm just going to plug it in here. So, and looking at this, that's the same as that. So that's just x minus g over 2, and then I just need to square that. So 2x squared over v squared. The 2's cancel. And there we go. We've got the equation of the trajectory because we've got basically the equation of y in terms of x. Yeah. Sometimes I even notate this as s little x, s little y. So I can basically saying the displacement from an origin, from a common origin in the x direction, and the displacement from a common origin in the y direction. And perhaps it would be a bit more obvious what I was doing here, but that is the equation of the trajectory of P. That's what they mean, the path that P takes in terms of y and x, well, y in terms of x. Okay, the point of projection, the origin, is on the floor of a barn. The roof of the barn is given by the equation y equals x tan beta plus, x tan alpha plus b. Interesting. Okay, so let's try and draw this on my diagram, the barn roof. Now, can you see, unless I draw this angle as smaller than that angle, there's no way that this object could actually touch the roof, yeah, which is what we're doing here. So, don't go on your diagram making it like this, because obviously that's never going to touch that roof. That comes in really handy in this part. Yeah, where we have to justify our choice of the negative root. So it is important that. So I'm going to draw it like this, like it's going to hit. Then I'm going to just, sort of like dot, dot, dot the path of this. So it just touches here, so it touches there, say. Okay, that's what's going on. And this is y equals x tan alpha plus b. Whereas the other equation, well, we just worked it out, is y equals x minus gx squared over, what was it again? V squared? V squared. Okay, cool. Now, we want these two to touch, yeah? So you might start by thinking, let's try and solve them, yeah? But remember, you don't need to find out where they touch, you just need to make sure that they touch. Remember also that touching is not the same as passing through. Passing through is where it'll go like actually through the roof twice, but touching means it's tangential and it just brushes, if you like, once, which means my quadratic equation here in terms of x should just have one real root. Yeah, so I'm going to firstly rearrange it so it looks much more like a quadratic equation. So gx squared over v squared plus x times tan alpha minus 1 plus b equals 0. If that just touches the roof, then this should have just one solution. So what I'm going to use next is that b squared minus 4ac, which I'm going to put in commas because I've already got b with a very different meaning. So I'm telling the examiner what I'm doing here. B squared minus 4 equals 0 as it touches, yeah, and hopefully that will convince them that I understand that there's only one solution here. It is nice to let the examiner know what you're doing, yeah, because reading somebody else's maths is actually really tricky, and so you know you want to make sure you know what they're doing. Otherwise, I mean, you know, when I'm marking students' homework, quite often I'll mark something wrong, which is in fact right, and it's often, and I don't mean to complain about the student here. Sometimes it's just through my own carelessness. 100% of the time, that's yeah, that happens, yeah. But sometimes it is just because the student hasn't really explained what they're doing, and there's just cryptic jottings all over the page. So, you know, let them know what you're doing. It's, you know, check the step examiner reports. They say exactly this. They say, please let us know, you know, with a diagram or a few words what you're doing. So do let them know that. Okay, b squared. What's my b squared here? It's tan alpha minus 1 all squared minus 4 times by a, which is g over v squared, times by c, which is b. So let's just put a b there and get rid of that. Okay, equals 0. What I'm going to do now is I'm going to try and rearrange this into the answer. I'm going to times through by v squared first. And I'm going to move the 4GB to the other side as well, actually. Because then I can just see I'm going to get what they need. Square root both sides. And I'm going to get 2, I've square rooted that, root GB. But remember, when you square root, you get a plus or a minus. You get two answers there. It's a bit like, have you ever thought about what the graph of y squared equals x squared looks like? Well, because when you square root, you get y equals plus or minus x. You do actually have two straight lines to draw if you start with y squared equals x squared. Yeah, because y equals plus or minus x. So don't forget the plus or minus. Okay, now, justify the negative root. Well, the reason why we have to take the negative root is because, as I was saying earlier, alpha must be less than 45 degrees or it can't touch the roof. Yeah, and that's just through common sense, really, looking at my earlier diagram. Yeah, if that's a greater angle than this, bearing in mind this gradient's just getting less and less steep as we travel along the curve, there's no way it could ever get to a point where it had a greater gradient than what it started with. So this alpha, which is, let me just show it on the diagram because I don't think I've annotated it yet. There's alpha right there. That must be smaller than this angle of 45 degrees here. Now, once you see that, you'll know that tan alpha, therefore, must be less than 1. Because tan of 45 is 1. So tan alpha is less than 1. Therefore, right-hand side is positive. Sorry, left-hand side, sorry, is negative. So right-hand side is negative, and minus 2 root GB should be used. There we go. Something like that. Hopefully, they'll let us use that. Remember, they're just looking for somebody who knows what they're talking about, who isn't fluffing the answer. Tell them exactly why you think that should be the case. Okay, so we've done that bit. If this condition is satisfied, find in terms of alpha, v and g the time after the projection at which the touching takes place. Okay, so when does that touch that? Now, you've got choices here. I suppose you could try and find x. I'm not interested in that way of doing it. I'm going to do it like this. I'm going to note that when it touches, if it touches, yeah, and doesn't go through twice, well, when it touches, it should have exactly the same gradient as that line here, yeah, which is, now remember, the velocity as it travels around the curve, like the velocity will help you find the gradient as it's moving, yeah. We want that to be, let's just write this down. So to find time, note that, okay, what have we got? U is v over root 2, v over root 2 still. A is still 0 minus g. V, though, this time is what I'm going to use. I'm going to say it's going to be k cos alpha and k sine alpha, because then it's going to have exactly the same gradient as the tan alpha one, yeah? Because we basically want the velocity vector to be exactly parallel to the roof, yeah? Here's the roof, which is, alpha, where tan alpha, that's basically alpha. Tan alpha is obviously sine alpha over cos alpha, which is, opposite divided by adjacent. And so, yeah, we want our velocity vector, which is like this, to be k cos alpha, to make sure that that angle is exactly the same, and k sine alpha. I have to use a k just because velocity obviously doesn't have to be exactly the same value as whatever tan alpha is, like or it doesn't have to be exactly the same value. It could be any scalar multiple of that. It's just in the same direction. Yeah, think of it like that. It's just in the same direction, so it should be k sine alpha, k cos alpha. Okay, what I'm going to do now is I'm going to find a time. T equals question mark. Yeah, this is how I often set up my SUVATs when I'm doing projectiles. I just do three vectors, well, three possible, yeah, basically I write down 4 letters, 3 of which I know and 1 which I don't know. Okay, so v equals u plus at, so k cos alpha, k sine alpha equals v root 2, v over root 2, v over root 2 plus 0 minus g times t. So in other words, k cos alpha is v over root 2, that's cool, whereas k sine alpha equals v over root 2 minus gt. If we divide these two, we get rid of the k's and we end up with tan alpha is v over root 2 minus gt divided by v over root 2. Apologies for that little splodge there. Get rid of that. Okay, so now all I'm going to do is I'm going to rearrange this into t equals, yeah? So I get v over root 2 tan alpha minus v over root 2, if you like, equals minus gt. And so t equals v over root 2g, that's right, it's g root 2, multiplied by, well, we'd have tan alpha minus 1 when I factorise it out, but I'm going to change the sign on that to make it 1 minus tan alpha. And I think that should be correct now. Okay, that's the time when the intersection takes place. When it just touches the ceiling. Okay, a particle Q can slide along a smooth rail. So this roof now becomes a smooth rail. It's projected from a speed from the point B, 0b, which is exactly where the roof starts, with speed u at the same time that p is projected from the origin. Given the particles just touch in the course of their motion, show this is true. Okay, the last bit's often a bit harder, and that's fine. If you don't get every single part of the question, if you're getting sort of like 3 or 4 really good answers in step, and then last 2 you're kind of getting half of it right, I think actually that's a fantastic performance, and you could do very well with that. But yeah, anyway, let's show how we do it. So just consider the particle on the rail first. Remember, this isn't a projectile, so you can't use the same kind of methods. Yeah, it's been projected with speed u, and I'm going to go in this direction first, yeah? I'm going to find the acceleration. If this was mg, well, that would be alpha, because that's alpha, and that would be r. And so you definitely could say minus mg sine alpha equals ma, and that's from f equals ma I'm using there. The m's cancel, and we can see the acceleration in the diagonal direction is actually like g sine alpha in that direction. That's the acceleration, yeah? Or minus g sine alpha. So u equals u. A equals minus g sine alpha, yeah? And what else do we know? Well, we can actually work out the displacement as well, because if we think about what we're doing here carefully, can we see that we've got, let me just think, what have we got here? Let's have a little look. We're going to have, yeah, S equals let's just put down t equals t here. So s equals ut minus g over 2 sine alpha t squared, yeah? And that would be my displacement in terms of t. Remember, actually, I know t because the time taken to slide up the rail is the same as the time taken for the projectile. So actually, this is going to be what your t is. But let's just leave it in terms of t at the moment. Now remember, that's the displacement in the diagonal direction, yeah? I should point out that all of these are in diagonal directions, yeah? If I wanted to just find the component in the x direction, all I need to do, because it's also an angle of alpha, yeah, well, let's just multiply it by cos alpha. Then the x direction, s little x if you like, is cos alpha ut minus g over 2 sine alpha t squared, yeah? That's how far this has gone in the x direction for the rail. Now we've also can do exactly the same thing for the previous particle, the projectile. So let's just put for projectile, we've got u equals v over root 2 v over root 2. You've got a equals 0 minus g. You've got s equals, well, we're looking at sx, sy here, but I'm interested in sx and t equals t again. So you're going to have sx equals just v over root 2t. So we can say that one equals this one, yeah? That's what we can say, because the displacements in the x direction should be the same. And then basically this ranges into the answer, yeah? Because look at what you've got. You've got cos alpha, right, ut minus g over 2 sine alpha t squared. It's not hard though now. Once you get to this point, it is not bad. Okay, cancel everything by dividing by a t and multiply through by cos alpha, yeah? So we get u cos alpha minus g over 2 sine alpha cos alpha times by t equals v over root 2. Yeah, I've divided everything by t and I've times through by u. Did I times through? Sorry, I've times through by cos alpha. Yeah. Okay, now if you look at their answer, they're saying what we've got to prove starts 2 root 2 u cos alpha. So I'll times everything by 2 root 2, I guess, because that's what they did. Okay, so we get 2 root 2 u cos alpha minus, okay, this is going to become root 2 g sine alpha cos alpha. But let's write t in terms of what it equals according to our last part's answer. It was v over g root 2 1 minus tan alpha. Okay, v over g root 2 1 minus tan alpha. 1 plus 1 minus tan alpha. Cool. It's kind of in the way now. Let's get rid of that. And that should equal v over root 2. Yeah. Okay. I'm now just going to put all of this onto the right hand side and hope for the best. Now what have I got here? Have I actually, might be wise timesing by a root 2. Well, that root 2 is going to cancel with that root 2. Let me just check I haven't made a blunder here. Where's my g over 2 gone here? Look at this. I don't think I've got rid of that. I think I've ignored that. That should be g over 2. Because I times that through. Where'd this root 2 come from? Sometimes as I'm talking, I actually get things wrong because I'm talking. Let me just check. I times that by cos alpha. That's u. Yeah, I divided through by t. It's helpful if you tell yourself, because otherwise I'm going to make a mistake. U cos alpha, and then there should be a cos alpha here. Yeah, that's g over 2. And then I timesed everything by 2 root 2 here. So I get rid of the divide by 2 and need to add a root 2. Cool. Okay, brilliant. Oh, and that's why if I times by root 2, that should be 2v now, because I times by 2 root 2. I'll get there in the end. You know what it's like, it's easy to make little blunders. So I got rid of that. Yeah, that looks good, because then now that's going to cancel with that, which is lovely. So 2 root 2 u cos alpha equals v times by 2 plus, Now, when you times this out, the g is going to cancel with that bit. Yeah, that's lovely. Root 2g cancel. And we're going to have sine alpha cos alpha. And then this is actually going to be a minus, because minus becomes plus. You're going to have a v, which is good, but I'm going to factorize it out. And then you're going to have a minus. Now, what's sine alpha cos alpha times tan alpha? It's sine squared alpha. And that's why the answer pops out perfectly then. Check that last bit of maths, but I believe that turns into a minus sine squared alpha. And you've done it. The result is shown to be the case, yeah? And that's it. That's that one. That was my effort on it. I hope you enjoyed that. A bit different from the other two I've done on Step recently. The other two have been pretty straightforward, really, provided you're happy drawing big, complicated polyhedra. It's not that bad. This, I think, slightly harder. However, looking back at it, once you get really, there's definitely some really hard A-level projectiles questions where we do similar kinds of things to that. I think that's harder, obviously, but it's not that different. It really isn't. It's not that big a jump. So yeah, projectiles, maybe that's something you'd like to pick on the step. Give it a go. Let me know in the comments if you're definitely going to go for the projectiles question. Okay, all the best and bye bye.